Good morning, everyone.
Hello.
Good morning.
I suppose I should say good day, or maybe even, depending, good evening. There needs to be some kind of time neutral way of saying hello. Perhaps good 24-hour cycle, everyone. I like your suggestion, Adam. Good now, everyone. What do you think, Sage? You want to start us off here with pull requests? I think at least a couple of these are yours.
Yeah, let me see. Look at the list. Let's see. Okay, so new stuff. Igor has a new pull request that has a second thread for KV Smith that he has good results with. I think he's going to talk about that in a bit. There's a patch in FileStore that I've been ignoring so far, but should probably look at. Generally not super excited about making changes to FileStore at this stage, but we can see there's a PowerPC CRC optimization. Kipu's looking at it. And I have a pull request that redoes all the deferred writes in BlueStore and makes optimizations. This is all sort of triggered by Nick's use case that I think is ready to go through testing. I need to address Igor's last set of review comments, and then once the lab is back up, we can run that through. See a few things merged. There is a async messenger useless ACK message that was fixed by HowMai. The wall option is merged, although it's not very performant yet. And there is a merge in FileStore that just avoids some in-memory copies in detransaction. Let's see, the HowMai has a pull request that uses the rocksdb command for removing a range of keys that we should probably start using. We'll need to do a little bit of testing because it's unclear, I think, how fast that's going to be in rocksdb versus enumerating the keys and deleting them individually. But presumably once they do the right thing, it'll be better. And there's still a pull request that does all the sync commit stuff that I'm planning on looking at as soon as the deferred write stuff merges. And actually, probably after Igor's 2 KV sync thread, after that merges too, I'll probably do that first. They're all sort of colliding on the KV sync thread in BlueStore, so I'll do those in order. And that's it. There's a bunch of stuff that's still in progress. Redislav has something in the bitmap allocator. And there's a prioritized recovery thing from OVH folks that I think needs a review still. That's mostly it on the pull request front.
Maybe Igor can go with some of his stuff, and if we have time, Sage, you could talk a little bit more about some of the work you're doing both on the Arrowhead log modifications and also the crush remapping.
Sure, and I think Alibaba wants to talk about their fast dispatch performance testing too. Let's do BlueStore first, and then we'll do Alibaba.
Okay, cool. All right, Igor, take it away.
Okay, hi folks. Let me share my slides. Okay, do you see anything?
Yep, it's working.
Okay, so today I'd like to share all the information regarding standalone BlueStore performance that I gained for a while, as well as some optimizations that we can apply with pending pull requests. So the first question I'd like to cover is how BlueStore metadata caching impacts the performance. Then proceed with how we can improve that caching effectiveness by optimizing blob and extend reuse. Then I'd like to highlight some potential negative impact from object content caching. And finally, I'll share the results about improving write performance by splitting KV sync thread into two parts. All my benchmarking was made using Ubuntu, pretty powerful Intel platform that has 48 cores and 128 gig RAM and 2 SSD drives. So I'm doing my benchmarks against all flash configuration. Actually, I have a single SSD for KV and write-ahead log, and another one for block storage. Also, as I mentioned, I am using standalone BlueStore, that is a plugin for FIO. I have 64 jobs, and I dev set to 16. And BlueStore is preconditioned with 128 gig of data using 4K sequential writes. And actually, I have two simple test cases. The first one is random 4K reads over 32K objects, with each one is 4 meg. And the second one is random 4K overwrites to the same objects. Well, for reads, I use the preconditioned image for all of test cases. For writes, I perform the precondition each time I repeat the test case. So, speaking about the code base, I use master branch. My pull request 13337 that refactors blob usage and extend map. Actually, this pull request attempts to reuse blobs and extends on override operation handling instead of creating a new extend entry or a new blob entry. And this results in less entries in extend map, as well as less in-memory footprint for runtime data structures, less overhead for serialization, deserialization, and as a result, we get better metadata cache effectiveness and performance. And another pull request that mainly affects the write path, it was originally proposed by MyJapan from Intel. That splits BlueStore KV-Sync thread into two parts. Actually, right now we have this single thread that performs both KV commits and completion afterwards. And since KV store seems to be the bottleneck for write path, it makes sense to load it as much as possible and having completion stuff in the same thread and performing commits and completions sequentially might affect the performance, and indeed it does. So I'll share the numbers that I can achieve by splitting that into two parts. Any questions so far?
Nope.
Okay, so let's start with 4K random reads against master branch. I considered well, several cases, well, different cache sizes at BlueStore, and raw device performance measured by FIO as well. So on the first chart, you can see that in my environment, raw device performance for random reads is pretty close to 300 megabytes per second. And when I have 100 gigabyte cache at BlueStore, I can achieve, well, pretty good performance comparable to my raw device, still less, but well, it's okay, not that much. But when we reduce the size of the cache, performance reduces dramatically. And in fact, there is no much difference between no cache case and 2 gigabyte cache. And on the right chart, you can see the hit ratio that was measured for each of the case. So for 10 gig cache, we can feed all the object metadata into the cache. And in fact, when I tried to measure the amount of memory for single object metadata, it appeared that it's pretty high. So it was about 400K for make object, about 10%. And
using the default metadata data balance on the left. It's like 90% metadata and 10%.
No, it's 100%.
Mm-hmm. Okay.
So after that, I started reworking of these data structures. Well, there were some commits that reduced that, but the major one is this pair pull request 13337 that I said attempts to reuse extents and blobs instead of on overrides instead of creating new entries. In fact, it reduced the single object metadata footprint about 10 times. So it's about 32 kilobytes at the moment. Well, depending on so there is a max target blob size that actually affects this size as well, but well, the reduction is dramatic. And on the chart, you can see that the test cases with less cache size gain the similar or even better performance for it, as well as they obtained increased cache hit ratio. A side effect of this change is also the improvement of read performance improvement for no cache size. And an interesting thing here is that cases with less cache sizes show a bit better performance comparing to 10 gig cache. So I did some investigation on that, and it appeared that even if we have 100 ratio for metadata caching, if we have free space at the cache, object content is also cached. And there is an issue that causes memory duplication when we perform single page memory allocation. In fact, allocators in this use pattern allocates 2 pages, and moreover, they are not measured properly by mempool staff, and hence BlueStore attempts. It allocates even more memory than the specified limit. And moreover, the runtime data structures for this content caching seems pretty complex and heavy weighted, so it looks like they affect performance as well. The test cases with disabled buffered read mode that actually disables object content. And here you can see that performance for all caching cases is pretty the same. So these green charts.
Is this like an NVMe SSD or like a
no, that's SATA drive. NVMe, okay. Yeah. Well, I just grabbed the NVMe drive, and actually, I have some preliminary results, but I decided not to share them yet because there are some inconsistencies.
Yeah. I wonder if we should just a simple thing might be just to set like a different default for the buffered read, if it's an SSD, or even just like force that to be always off.
Yeah, maybe.
The memory isn't going to be significantly faster than the SSD in these cases.
Actually, we can take a look at this object content as well, object content caching as well, and probably refactor something there. I haven't did that yet. So.
Yeah, awesome.
Okay, now similar set of test cases for 4K random overrides. So first of all, for master branch, and here you can see, again, pretty significant dependency on the cache size. And moreover, you can see that write performance is much worse comparing to the raw device. Even comparing, if for read case it was pretty close, for large cache size, here it's still more than double less. Now I applied my pull request with blob reuse stuff, and as expected, I gained the benefit for lesser cache sizes, and performance became comparable to 10 gig cache. Then I did this buffered read mode off, and actually got no results, and that's as expected, since there are no reading, content reading on writes, so no benefit from that. And finally, I applied the mentioned pull request that splits the KV sync thread into two parts. And well, actually, results were pretty surprising. So I got about 2 times improvement for cached size cases, and well, pretty significant improvement for no cache as well.
That's awesome.
Yeah, actually, I still not completely believe in these results, so it would be nice if somebody can verify that. And,
Igor, as soon as I've got access to the lab, I'll go through and check this. But it's not that unbelievable, though, right? I mean, we've kind of suspected suspected for a while that we're just everything with like 4K random writes like this is bound by how quickly we're dealing with RocksDB.
Yeah, but it appeared that completion stuff, well, is probably comparable to, well, latencies there are comparable to RocksDB. That's surprising, and probably worth to more investigations. Well, any more questions so far?
Nope.
Okay, so actually that's all of my performance results, and some conclusion that I have are about object metadata effectiveness, and actually it's pretty useful if used properly, and well, if you have high cache hit ratio, they are good enough comparing to SSD performance. And actually, we need to have these changes in metadata footprint, memory footprint, to use cache effectively. And also, we should care about that content caching, since it might have some negative impact, at least in some scenarios. And well, that's a good enough workaround to disable buffer treat sometimes.
Yeah.
And well, speaking about write performance, well, I believe there are more space to improve here, but well, original numbers are pretty poor, and well, especially in case of no cache. But with all these pull requests, it might be a bit better.
Yep, a lot better, it looks like.
I'm curious. Oh, go ahead, Sage.
That's it. Go ahead.
I was going to say, I'm curious if when we've been testing on our NVMe devices, if we have enough backend throughput that when we that is kind of hiding this. That maybe this is showing up because you've got a device where you can really saturate it.
Well, speaking about NVMe, I can say what I saw when doing my brief benchmarking. So with all these pull requests embedded, I could see about 2 times less performance comparing to my raw device that is Intel P3700. And speaking about write performance, it was still Well, about 4 or 5 times less.
In the cache or the no cache case?
In case of cache size, for no cache, it's even worse.
Sure.
Yeah. Yep. Yeah,
well, I don't like the performance numbers for this raw device itself. It appeared to be pretty high comparing even to Intel specs. So I decided not to share that. I need to do additional benchmarking, I think.
The P3700s that we have in the lab, I think Intel claims can do around 60,000 write IOPS, if I remember right, the size that we have.
Yeah, something like that, but I could see about 800, and that's
okay.
That's wrong,
yeah.
I think.
Yeah. So with BlueStore in the past, I think I've been able to push somewhere around. Well, it changes depending on which particular version of BlueStore we're talking about, but I've seen like 15 to 16,000, and at one point I think we were maybe hitting more like 20 or 24, but that might have been under special circumstances with some PRs that weren't merged.
Mm-hmm. Okay.
Well, actually, that's all from my side. So,
okay.
Any questions?
This is great. I can't wait to review and test this stuff. Yeah. Yep. Very excited to get this.
Igor, what do you think of the so Somnath a while back had this kind of like multiple KV sync thread PR. How does that interact with this other one, or does it even interact with this other one that you have?
Well, I did a brief try some time ago and didn't see much difference, but that was a bit different patch since it didn't split the functionality of the thread. It just multiplied the threads themselves, and well, I think that's a bit different use pattern, and this might be the root cause why.
If I remember correctly, Somnath was saying the same thing too. When he was using RocksDB, he didn't see much difference. It was only when he was using the Zetascale backend that it was noticeable.
Yeah. So it looks like we still we are still locked at RocksDB, and more threads to commit data doesn't help in this case. But when we split the thread, we can just commit more. Well, there are no gaps in committing data to RocksDB, and it looks like it helps.
Did you test small sequential writes at all?
No, I didn't try any small writes or reads. Well, when I was preconditioning the image, I did the sequential writes. Well, I could see performance improvements for writes as well, but well, I didn't collect the numbers.
Okay.
But it was about 50% to 100% similar to these write cases.
Cool. Were you at all pegged on CPU, or did you still have CPU available?
Well, since I had plenty of cores, I didn't care much about the CPU. It was pretty high; it's about 1,000%. But well, since it was 48 cores, that wasn't an issue. So, speaking about my benchmarking, it was probably mainly about scalability rather than performance. So it looks like we are facing some scalability issue. We can't scale even if we have computation resources. They don't help.
I guess maybe more kind of what I was wondering is once you were able to get past this with, especially on the right side is what I was kind of most interested in. Did you see like a linear increase in CPU usage associated with the performance increase?
Well, I didn't care about that.
Okay, okay, that's fine. I'll look once I can try to replicate your results, but that'd be good to know.
Cool. All right, I want to make sure that the Alibaba folks, I think James is here, have a chance to talk. They want to talk about the fast dispatch testing results that they had. So let's do that next, and we'll do.
Yes, Sergio, we are here.
Cool. Go for it.
Okay, I'm going to share screen, right?
All right. Thanks.
Oh man, I need to add an extension. Hold on. Okay. Okay.
I think you can.
There you go.
It's okay to see our screen now?
Yep.
Okay, here is pretty much the experiment we did for the fast dispatch. And the background for this experiment is right now we have a cluster, pretty much all the cluster with MME drive. And each server going to have a 12 MME. And so far, we only have 5 servers set up for this test. But eventually, we're going to have a way bigger cluster with MME drive with Ceph cluster. And here, yesterday, we also discussed what kind of code we are running using. So basically, we're going to have a fast dispatch. This is one, and we have a parent branch. You can have a comparison of this code. And we also have 10 terabytes IBD image. We create a 10 terabytes IBD image. By the way, we are actually right now using NBD plus NIBR-BD. And the background for this test, actually, we try to utilize all of their method or all of their patch as much as possible to improve the performance. Especially, we care about the latency and the fault line latency, because we actually right now use the Ceph cluster for OLTP kind of workload. And the hardware wise, frankly to say, we are okay to use the most I should say most performance intensive storage like a MME device. It's okay for us, but their latency, tail latency, and their average latency is pretty critical to us. That's the background. Of course, today we just share with you guys of the performance bench we get from Sage the commit regarding to the fast dispatch. Here is the we benchmark a different perspective as far as you can tell, because we do have a report from Mark Nelson. Actually, last time you get for the fast dispatch, but you probably more focus on the IOPS and throughput. But this time we more focus on their latency and their average latency and their fault line latency. Does that make sense?
Yep.
Okay. So right now we have tried different jobs. Of course, here you can tell from the data, a difference between the fast dispatch and without fast dispatch. We can see for run and write, the difference is pretty small. They only have like a 3.1 to 2.8 difference. So far, we are going to run the fast dispatch in way bigger cluster to see whether this difference is kind of outlier or not. But for the fault line latency is pretty significant, especially for 16K and 128K. They almost have 20% difference. So I was not sure whether Sage or Mark Are you guys think this is normal? I think this is good for us, but there are we just want to make sure from theoretically is that normal, or we going to have a different, you know, we are not sure whether it's going to be outlier or not.
I'm sorry, which exactly which part are you asking about? You're talking about whether these raw numbers look about right ballpark?
The 4.9 latency. Do you see the 4.9 latency when we do the random write and the block size is 16K? We see the with the fast dispatch, we see the tail latency drop to drop almost 27%.
So we didn't
Go
actually we weren't able to do this test really. We just sort of assumed that it was going to be better, but we didn't actually demonstrate that it was better. So this is very good to see. So it means it worked. But we didn't actually show a difference.
Okay. Yeah,
we weren't measuring
carefully. The only thing we worry about actually is the 4 mega, because as I said again, block size 4K, 16K, 112K, and 4 mega is pretty. It's a pretty typical workload in our environment. So we have tried this 4, but we didn't see the 4 mega drop or not. We don't know why.
Yeah, that one I don't really understand either.
Okay.
It looks like the average. So it looks like the average is down, but the 99.99% late percentile.
The average latency is also down a little bit. This is good. This is good because, as I said again, we're also looking for the average latency down as well.
How long were your tests? How long did they run for?
Hey, me?
So in each, sorry, what was that?
Oh, we run almost 1 hour.
Okay. For each one?
For each one. And we don't know yet whether the cluster size is going to determine the latency. So the next step for us pretty much going to move the fast dispatch experiment to the way bigger cluster to see whether they're going to have a similar performance or not. But anyway,
and I almost wonder if the 4 meg result is like a secondary effect, that because the average was slightly lower, then as it ages, you just fill up more, and there's sort of a normal utilization degradation. That's what we're seeing.
That's possible. It's possible, yeah.
It'd also be interesting to see what the average, not that it's easy to do this, but to see how many IOs are, how high the concurrency basically is, right? So if there's more stuff getting thrown at it, maybe it's bumping that up a little bit. Like some things are just waiting a little longer. But your throughput might not be any different, which is for 4 megabyte writes. That's really what you care about, right? But we also have numbers?
We also have a throughput number. We can go through it later. We have a throughput number. Okay.
Yeah, it might not really matter.
But okay, so this is a random write, and here is a random read latency, and we have a big problem because most of the case the first of all, the average latency is still good. At least it's down from 4K to 112K. They down average wise 3%. But the 4.9 latency actually is up on more. So 4K is 4K.
Sorry, it's kind of hard to hear you now.
It's okay?
I think it's better, maybe.
I think that somebody should mute.
Yeah, here, just 1 second. Let me see who else is on here. And mute Sage, just make sure it's not him.
Hi, James. This Ming. Could you move to the next slide for random read?
Random read and latency.
Yeah, I didn't see your which page are you at now? It's page 4?
It's page 4, yes.
Oh, I only see page 3. Anyone see page 4 now?
I'm still seeing 3 as well.
Okay. Can you see the page 4 now?
Yeah.
Yes.
Okay, cool. Okay, here is a random read and latency. The 4.9 latency actually is a wire song, especially for 4 mega. It's up significantly. And this is very interesting.
Wow.
Weird.
Yeah, but the random read and latency actually is still down. This is good. So we right now try to make sure the 4.9 latency we measure is not going to be outlier. That's the reason why we later on going to do more experiment in some of our bigger cluster and see whether it's outlier or not. Okay. So okay, here is a sequential. Okay, go ahead. Guys.
Oh no, nothing. Go ahead.
So here is our sequential write latency. So the sequential write latency actually is okay too, because it's pretty much same as the random write. But the only thing, as I said again, is still 4.9 latency. The 4K actually is up. So we are not sure right now it's outlier or not. So we still need to do more benchmark to see whether it's outlier. Otherwise, the average latency is drop. It's okay, even though not drop not that much, but still drop.
One question for you. In the 99.99% latency, how many samples do you have from each of these? Like for 4 megabyte writes, how many actual IOs do you know?
Well, here we have I mean, do you know how much IOs we issued?
I didn't record the numbers, but if so, yeah, I didn't record it. I didn't have the exact number now. But for the test case, we are running one job, one IO depth to measure the average for 99 latencies. Sorry, are you asking the whole the throughput or the whole IOs?
Well, I guess what I was wondering is for 4 megabyte writes, obviously there aren't going to be as many of them for a particularly timed test versus 4K writes. And if you're looking only at the 99.99% latency, I'm just wondering if maybe the sample size is really small.
That definitely makes sense. Later on, when we do the experiment, let's connect all the data we write into the device. Then we can calculate how many objects we write into the device. We will do connect this data later. Okay, here is a random write IOPS, and I'm not sure whether this one actually similar as what Mark you observed with your experiment. For us, 112K and 4 mega, the IOPS actually is up, but for 4K to 16K is drop a little bit. So Mark, do you have any comments?
Are these the same tests where now the IOPS is lower, but your latency was also lower?
The IOPS is this is the same test. This we just get the result from different perspective. So for example, for the random write, IOPS right is up, but you can see the random write latency is down as well.
Yep.
Average noise. Right, but there's
Well,
some.
I mean, they're different runs though, right? Because you've got different I/O depths and numbers of jobs.
Okay.
Yes.
Yeah.
Yes.
Okay.
Yeah.
Yes. Sorry.
What could be interesting is to look at the latency and the IOPS at the same time
Okay.
and see what's happening.
Okay. Cool. Yeah, later on we will do the same thing. So here is the random read IOPS. We do see we pretty much see the random read IOPS up all the time. So from 4K to 4 mega. This is good.
Mm-hmm.
But for second read IOPS, 4K wise is up, but for others they drop. Yeah, I think this is pretty much the initial experiment we have so far, and later on we're going to do more experiment, especially we're going to observe more their latency, because we care more of the latency. We're going to do more observation of the latency, especially average latency F49 with bigger cluster, and going to share with you guys soon.
Okay. Yep. This is yeah. Thanks for doing these experiments. This is definitely helpful because we didn't actually demonstrate much of a difference at all. I do worry that some of these cases where you're showing like less than 1 percentage point or 2%, I worry that this is just noise.
Yes.
And that we shouldn't read too much into it. Especially the 4.9 latency, that's going to be pretty susceptible to noise between runs. Like I wonder if the order that you ran the tests in meant that they're aged differently, or maybe the garbage collection in the SSD kicks in at a different time or something. Like any of these factors could have a pretty significant impact. I imagine it's such a small change. I wouldn't expect any impact really on a 4 meg IO because it's just changing the queue handoff. And like if you look at the small IO sizes, it's a pretty consistent like 20 to 30 microsecond latency difference. And that's nothing when you're talking about a 4 meg IO. So unless we like accidentally made some other change in that branch that broke something else, I have a feeling that the other ones are noise. But it'd be if you can repeat and maybe do it in the opposite order, like do faster and then without, or whatever you did before, we can hope that the 4 meg thing goes away. But if it doesn't, then we should probably dig in deeper.
Okay. Okay. Cool.
So that's kind of why I was wondering about the sample size too for 4 megabyte reads like this. With a 99.99%, you're only looking at that portion of the IOs. There's probably not very many samples. So if you happen on a bad one,
Yeah.
Okay. Yeah.
Hi, I said listen Ming. So a general question about the patch. So we did read the patch, and looks like the main thing it did was to optimize the IO request in QDQ thing, right? So I think any improvement or large length, for example, 10%, it doesn't make sense, right? Because the patch only optimize the in-QDQ things. It should not make a bigger change to the whole IO stack, right? It didn't. It didn't make a
right. Exactly. I think. Yeah. Sorry. Go ahead.
So I think that we should only expect for example, maybe 5% change, either better or worse, right? This number more makes sense, right?
Yeah, I think so. There's one of those plots. It was where you're looking at the actual microsecond latencies. I think a 20 to 30 microsecond number makes sense, given that the tests that Intel did several months back were showing that whole enqueuing part of the workload was, I think, in the neighborhood. I think they showed like 40 or 50 microseconds total in the time spent during fast dispatch. So if we cut out most of that, that feels about right, sort of given what I would expect. Yeah, I guess this is the number here. So here you got like 18, delta of 18, and then 10, and then 7. Yeah. So I mean, you can see the difference there. I think the one above the page 3 was one I was looking at before. If you go up here, is something similar. So you have like 20, 20, and 30. Looks like about what the difference is there. Almost 40. I don't know. Yeah. I mean, those feel like about the right ballpark, I guess. If I'm being optimistic, and we got rid of most of the work. So that seems about right.
Okay. Cool. Okay, thank you, Sage.
Awesome.
Yeah,
yep.
thanks.
Cool. Okay. Let's see. Does anybody else have any topics they want to bring up?
Actually, yeah. I just wanted to ask on the one thing regarding recovery and bringing up back OSDs back to life from any kind of failures. We have already fixed the issue when the OSD goes down for some reason and it doesn't get up immediately, so the IO stalls in that moment. But there's one more thing actually, which is when OSD goes back up and it announces its presence back to the cluster. We are observing some strange phenomena. You can see on this PNG I have pasted in the chat that once the OSD gets back up, it marks all his PGs as activating and inactive, and during that time, IO for these PGs, no matter which client has sent it, are always stalled, and for a few seconds up to a few minutes, we are seeing stalled IO on almost every OSD on the cluster, as you can see on this PNG. So the question is this a known phenomena or?
It's not supposed to happen. But I'm not completely surprised. So there are a couple of things that it could be. When the OSDs go up and down, and any particular PG is doing peering, then IO is expected to stall on that PG.
Yeah.
So there are definitely things that we can do to speed up peering and make it bypass a lot of its work in sort of the common cases. But I wouldn't expect IO to unaffected PGs to stall. So what it might be is that for any OSD, some of its PGs are going through peering and some aren't. And for some reason, the ones that aren't going through peering are also getting stalled because the file store is just being stupid. Which, if you look down at the bottom here, that you see the file store apply latency goes way up.
Yeah.
It might be that we're doing a bunch of other IO because of the peering, and that's
right.
Interfering with all the other IOs. And so that's my guess as far as what's going on, but I wouldn't expect it to last very long.
Yeah, it doesn't last long, but it's somewhat limiting in our case because sometimes we simply have to resort, for example, enter a host for some update or something like that, and then we have stalled IO for entire cluster, which is catastrophic in our case. So I was wondering if we can somehow minimize the effect of this phenomena.
Yes, I mean, certainly. So I think the first step is to figure out why what exactly it is that we're seeing. So I don't know if you have a test environment where you can reproduce this. If you can turn up the FileStore logs, then hopefully if we can reproduce this with logs, we can try to figure out what actually is blocking the IOs on the unaffected PGs. I think that would be probably the next step to just understand what's going on.
In our case, I think it's not more about unrelated PGs, but about all PGs that are going to be brought back up. And in our case,
okay.
it will be a lot of PGs, like a few hundred. So this is an issue for us.
Okay. So in that case, the plan or the hope is that the expectation is that the monitor is going to do the prime PG temp, and so it's going to install a PG temp mapping that sort of fixes the interval with the previous value, and so that peering will be hopefully not happen at all or fast, and then it can remap to the other values later. But it's I think, if you can generate a log and we can look at the specific changes that a PG is going through, then we can sort of figure out exactly what's going wrong and why. I think that's sort of the analysis that we just haven't really spent the time to do.
Another piece of data that would be good to gather is what's going on with the OSD maps while this is happening.
All right.
Yeah.
All right.
Yeah. So it could be that. So I guess for any given PG, there's probably an interval change, which means there's some peering traffic. But it might also be that it's doing a wait PG up through or whatever, where it actually has to wait for the monitor to make a update to the OSD map before it can go active. So we need to figure out exactly what it is that's blocking the IO, and we can then focus on how to address that specific thing. Because there are probably sort of optimistic expectations we can make and to try to avoid it, but we need to figure out exactly what it is first.
Since we are on Hammer, I'm wondering if this might be the case of the most of the PGs of the OSDs getting back up are setting back to activating state, and clients and other OSDs automatically see the state change and reroute clients to the activating PGs, which at this point don't accept the client IO and stall for that reason.
That's going to be part of it, but I think it's not really so much the client's fault. If the map has changed, then they should be sending the IO to the new location. The old OSDs aren't going to be able to service the IO. I think the way to address it either way is to make that activating interval as short as possible and make the peering happen quickly. And I think eventually we'll be able to make it so that the peering in these cases where there actually isn't a change in the acting set, it's just the upset that's changing, for example, then we should be able to make the peering sort of a no-op. And in the case where acting set is changes, we should be able to optimize it so that it's sort of in the common cases, for example, with a simple restart, then it's doing it as fast as possible. But either way, I think the thing to do is to reproduce this in a test environment where you can show that this effect with logs, and then we can go through and we can look at specific IOs that got blocked on what PGs and exactly what that PG is doing and why, and then figure out how to,
All right.
But unfortunately, there's some analysis that needs to be done basically, but I think that's the way to go forward.
All right, because actually I have an environment where I can have this phenomena visible, so I will just crank up the logs to the maximum and see what happens in that.
Okay.
In the C logs.
I mean, if it's a production one, you might not want to be able to turn the logs all the way up.
No, it's not production. Don't worry.
Okay. Okay, good. Okay, cool.
No,
okay.
We are not that crazy.
Yeah. Okay, good. And I mean, I think it would be nice if you could do it on Joule or master also. Although I don't know that there have been real big peering changes since Hammer.
Sure.
But eventually we'll want to be able to reproduce this on master and then demonstrate the improvement on master.
Actually, I think I will try this. I will try this on Joule because we are moving from Hammer already. So.
Yeah. Perfect. Okay.
Okay.
Okay. Great.
Great. Thanks.
Yep.
So here we still have one question regarding to the FileStore. Actually, yesterday we have a discussion with Greg. I think Greg already replied in the email, but the question is about so far if we're going to write, if we're going to use the FileStore, and FileStore for journaling, of course, they use a sync IO and also enable their OD sync. And we, of course, observe the latency is pretty high if we enable OD sync. And pretty much as answered by Greg in the email, all the time, when we write a journal, the journal always need to write to the disk or platter until they reply. It causes lots of latency, at least from our observation. We can say at least 500 microsecond add-on. And once so
Sorry,
here,
sorry. We mean five. Yeah. Oh, sorry. Go ahead. 5 microsecond. Yeah, right.
500 microseconds add-on. So we were wondering if our drive, first of all, is SSD. Second one is a PowerSafe, is enterprise SSD. They always have a big cap over there. So in that case, would it be possible to disable the OD sync?
So the only reason to ever disable OD sync or flushes is if you have a device that has horrible firmware that isn't smart enough to realize that a flush can be ignored. So if your device is in fact power safe, then it should be ignoring the flush. And if it isn't ignoring the flush, and it could, then their firmware is bad, and I wouldn't trust it. So basically, the only case where if you have a device that's power safe and you send the flush down, it should be a no op, right?
Mm-hmm.
And in fact, if you're doing OD sync, the kernel should be setting the FUA bit on the IO, so it isn't even an extra trip over the bus. It should literally just be one bit that's set on that particular IO.
Mm-hmm.
And so if the device is power safe and it's not, an idiot didn't write the firmware, then it should have zero cost. Like the setting the flag or not setting the flag shouldn't affect performance. If it does, that suggests that either it's not power safe or the firmware isn't smart enough to realize that it should ignore the flush when it should. And that makes me suspicious of the firmware in general. So the short answer is never disable flushing, ever.
Oh, okay.
Yeah. If you do have a device where it goes slower when you have flushing on it and the device isn't crap, then that's a conversation you should have with that vendor. And I'd be interested to hear how that goes. But as far as I know, the only time I've ever heard of, the only justification I've ever heard for disabling these flushes is it used to be that these high-end enterprise vendors just misread the spec. And so they had these battery-backed caches on their controllers.
Mm-hmm.
But they read the spec as saying the flush meant that it had to be on disk and not in a battery-backed and stable cache. But the spec doesn't really say that. The spec says it has to be in a persistent form, which would include their battery-backed memory. And so they just were making it so the flush was doing this work that wasn't really necessary. But that I don't think anybody does it anymore.
Okay.
So to my knowledge, there's no reason to ever disable the flushing.
Okay.
Yeah.
So
and if somebody finds one, tell me. But I don't think that's ever a good idea. And there's so many cases where disabling it is going to totally screw you because the device isn't actually power safe, and you're going to corrupt your data. So the risk benefit reward is like hugely skewed towards not trying.
Sage, to reinforce your point, there was a drive a little while back in SSD that was supposed to have power loss protection. All the marketing literature said it did. Everyone thought it did. This particular drive, it was found out later,
did not.
It did, but it wasn't big enough. They didn't have a capacitor to actually protect data in motion. So, It turned out in the long run that no, in fact, it was not safe to disable flushes on that particular drive.
Yep.
Okay, cool. Thank you.
Yeah. So I mean, I guess the thing to do is if you have hardware that you don't expect is crap, if you think it's good, and you just comment out that desync flag and you see it going faster, then maybe there's some investigation that's worthwhile to figure out why the device is behaving the way it should. But I would never ever run that in production. I would either get the vendor to improve their firmware, or give you a really good reason why they're in fact doing the right thing and we're all wrong. But I wouldn't turn it off.
Yeah, and actually we did measure with the all these things disabled. We did see about 200 microsecond improvement. So it's a lot. So yeah.
Okay. What device is it?
It's a SATA SSD.
It's a SATA SSD. From what vendor?
So we have a different experiment. Actually, we have some vendor name we don't some vendor as I said SATA SSD. We do see their performance improvement, and but when we try with the MME, one of the vendor MME SSD, MME SSD actually don't have this kind of latency. I think it is going to confirm what you said. So probably it's related to their device.
I mean, on a standard SATA SSD that doesn't have a super cap, like it's totally expected that you'd see a big difference.
Okay.
But it wouldn't be microseconds. It would probably be milliseconds because Flash actually is pretty slow. Yeah, what you might want to do is, it's possible. So I think probably the more likely scenario is that the way that ODSync is implemented in the kernel, it's actually resulting in one trip across the bus with the data, and then another round trip with a flush. And so there actually is some signaling delay across the bus. And the second round trip is basically a no up because the device says, oh, I'm power safe. I can ignore this flush. That's my guess. But I think, I guess I wouldn't expect that to be terribly significant. It might be that there might be a different way that we can use the interface so that it sets the few a bit on the existing IO instead of sending a second round trip. But you could confirm that by doing a block trace. So if you capture block trace with and without the OD sync and look at the difference, hopefully it's just the beta set and not set, but it might be that there's an extra round trip. So that would be helpful.
It could also be that if you're that extra round trip, if you're going over a SAS expander, it has to do the translation of SATA to SAS at the expander, and if it's already like full of other I/O and stuff, maybe it's a little slower than it would be if it was just a straight connection to the disk. I don't know how long any of that takes, but it what I guess popped up in my head.
Yeah.
Okay, we're going to go back to check with our vendor, and pretty much. Yeah. Okay, thank you.
Okay.
Hi, one more question. So if all the server behaves normally and no power lost, then we disable all these things. It should be safe for the data, right?
I mean, define safe. If there's no failure, then sure, everything is safe. You can write it to RAM, it'll be safe.
But
usually,
even let's only stop the failure, but no hardware failure, no power lost. From the software's perspective, it should be okay even with the old desync disabled, right?
Right.
Would you to make sure,
Yeah, but I wouldn't call that safe. I guess.
Okay.
Right. Yeah,
okay.
I mean, what happens is people turn off these caches, and then their PDU failures in the data center lose power to the whole rack, and then every single replica is corrupted. I guess I shouldn't say usually, but it does happen. So even if they have a UPS, if the UPS fails or whatever, so it's a bad idea. Unless you're just trying to understand what the system is doing.
Okay, thanks.
Yep. Okay. Yep. And let us know what you find out with the vendor, I guess,
Yeah,
or
sure.
block trace. Yeah. Cool. Okay.
Hello.
Anything else? Yeah.
If I may, one quick thing, I hope. We started some efforts related to performance, to CPU utilization in the beginning of BlueStore's pipeline. In the front end, it looks that we are, according to perf, it looks we are consuming a lot of CPU resources there. Single thread in product a single file tests using typical setup. 4 megabytes for 4 megabyte long objects, 4 kilo run threads is able to when the IO is enabled is able to get around 15,000 of kilo IOPS from really quick from really fast SSD. It looks that most of the most important bottleneck is related to CPU. You can overcome it quite easily when you increase the number of feeders. It's okay. However, I guess this is not a way to go into production, because in production I would expect that someone will really want to have put more than one NVMe or other super fast SSD per server. So we'll be definitely bounded by CPU, and in case of extensive caching, by memory. We would like to start some optimization targeting CPU resources consumption, and the linked PR is the first of broader series. The basic idea is to resurrect your idea with the basic approach is to resurrect your idea related to blobs serialized content caching, which gives significant improvement, and also to put some critical metadata like extent instances, like blob instances, into continuous memory. There is a allocator based on boost pool object. However, it's still not enough, I guess. I wonder whether is there any particular reason to have extent map T type def to boost intrusive set. It looks that the single instance of the extent class is very small. It's around 24 bytes on IMD64, and I would say that we can try to put extents to switch to STD vector, or whatever that provides memory, that provides continuous memory, that is friendly to CPU prefetchers. I can see a lot of cache misses exactly in encode and encode some function of the extent map class. It looks that we are spending.
Yeah, there's a boost flat map structure that works like a map that but uses a contiguous memory. It's like implementing it inside a vector. Something like that might help there too.
Great. I wasn't aware about that structure. Thanks a lot for the hint. We'll definitely take a look.
The one downside with flat map and flat set is that they require that the objects be inserted in sorted order to have decent performance. Otherwise, you get O of N with every insertion. So unless you can guarantee that, you're probably better off using intrusive set.
Guys, I think that modern CPUs are extremely good in memory copying. Moving 1 kilo moving 1,000 of 24 bytes long objects isn't really a problem.
I will be safe with that assumption.
I cannot agree.
To be fair,
CPUs are CPUs are really fast when it comes when they operate on local memory, when they operate on local caches. When it comes to fetch something that isn't in cache, when it comes to fetching from main memory, you are screwed.
This is the case with every CPU, so I don't see the problem here. More importantly, I would focus on doing large block copies and memory moves, because and this was the case in of the buffer pointers and the buffer list before, where we were copying small amounts of memory using memcopy calls. And this might sound fast, but in reality it isn't. So if you are going to target 24 bytes, you need to force compiler to optimize for this 24 bytes and not use some kind of automated assumptions.
Mm-hmm. My guess is that there are two cases to worry about here, specifically with the extents. One is the decode case where you're populating it. Just making sure that that's in order would make that sort of flat map issue largely non-existent, because then if you're doing a single IO or whatever and you're inserting one item, then there's just one move. It's not the n squared case. But the alternative implementation is that you use something like intrusive set, but then you use a boost memory pool so that all of the entries, even though they're an intrusive set, they're still going to be within the same L2 or whatever, within the same memory region adjacent to each other, right?
There will be, however, they will after a round of rinse writes, they will be okay. They will be in one region. However, they will be throughout in a random way across that region. And also that's the problem because prefetchers cannot work correctly in such environment. I have a performance. I have a listing from perf measuring LLC, last level cache misses, directly from my PMWin on my machine, and I can. It says to me that that we are losing a lot of resources, a lot of misses, to just housekeep the arbitrary structure that is under the intrusive set.
I've seen it too.
It sounds to me like the only way to really tell if it's going to work is to try. So I mean, you could probably pretty trivially just swap it out for a flat map and see what happens.
Cool.
And see what, I don't know, because they're competing effects.
It'd be really nice if, however we end up laying stuff out in memory, we'd be able to someday do SIMD encode decode on multiple things, because the way we do it now is pretty crappy.
Correct.
That would be great.
Cool.
Anyway, even putting the extent and object and blob instances on dedicated allocator that provides continuous memory gives around 130% performance of the reference case.
Cool. Yeah, is that the pull request that you pasted in there?
That is the one. Anyway, I made those testing without the branch that's the branch that splits KV thread, because I wanted to have the bottleneck in the front end exposed to me. Anyway, after applying the patch, I guess that similar results will be obtainable without omitting writes to block device.
Yep, that will save CPU time and all the rest. So, yeah, awesome. Okay, I will mark this one to take a look.
Radoslav,
also needs. Sir, please continue.
I wanted to quickly mention too that I did get a chance to test a number of your pull requests that you had. I think actually a couple of them have already merged, but I did see a certain amount of performance improvement with them. So I wanted to let you know. It was right before the lab went down, and I haven't had a chance to run anything additionally. But yeah, so good job.
Good to know. Thanks for those for these words.
Yes, absolutely.
Awesome. Okay. It looks like we have a feast of performance improvements here to review and test. So that's very good news. Thanks.
By the way, guys, what do you think about introducing a new method to buffer list? Method very similar in concept to write underscore fd. However, that could destroy the underlying data. Something like move fd. Write fd is supposed to keep the data intact. Move fd would allow us to save some resources when the data where the data aren't necessary anymore. Typical example is in rbd nbd utility main loop, where we simply don't need data anymore. However, we are still keeping them intact just to destroy them in a second later. Maybe that's not painful when using typical implementation of buffer lists. However, Adam Kupczyk made a good job in the area of a buffer list of a buffer lists instance, backed by pipes that allows to use splice, VM splice, T, and the whole zero copy function of family. Having move fd would allow us to save some syscalls, and maybe also maybe useful when dealing with regular buffer lists which are backed by memory. Maybe we would have implementation that also includes VM splice. I made some performance testing. In some cases, the performance boost is quite reasonable, around 20% or something. However, it depends on where you put the data. What is located under the underlying file descriptor.
I mean, it seems like a reasonable tool to put in the box. I think my concern is mostly just that we'd have to be very careful where we use it, because there are a lot of cases where there are hidden assumptions that the buffers remain intact, and they're sort of non-obvious until you sort of think about all the possible failure and retry paths and so on, that you realize that there might still be a live reference to the same buffer.
Maybe
so I mean,
we will be able to code to write that feature in a way using well-known functions like std_move or something like that, to make the fact explicit to anyone who reads the code.
Yeah, I think the trick is that I mean, if it's the buffer list itself that's being changed, that's fine, right? You can just make the function a non-const function. It's changing the buffer list. The buffer list itself isn't thread safe. It's when you have the list referring to buffers that have multiple references, so you have other buffer lists that are pointing to the same data, that you have to be careful. So I mean, you could make a condition on whether the reference count is greater than 1, for example, and that would be safe.
Yep.
But I think there are a lot of places where it's hard to tell whether there are other references to the underlying buffers. And most of the time it might be true, but in certain cases it might not be true, or whatever. So, but if it's a significant improvement in performance, then it'll be worth going through the effort to figure out identify those cases and make it work. So
sure.
Don't let that stop you. Just be aware that it might be harder than you think.
I will try. Thanks a lot. I'm going to write some blueprint, some short, really short mail to Ceph Devel in the end
Okay.
of this week. With some numbers related to possibility for possible performance gain for regular buffer lists, not
Cool.
not backed by Linux pipes.
Cool. Cool. Okay. Sounds great. All right. Well, we're way over. We should probably wrap it for this week. Thanks, everyone. And
Thanks.
have a good week.
Thank you. Bye.
Guys.
All right.
Well.
Bye, guys.
See you guys.